All right, my friends, let's take a look. So these problems were meant for you to be able to do them with if in doubt, expand it out. And so the truth is that, you know, a couple years from now, that's probably all you'll remember anyway. So let's see how part A treated you. So basically part A, all the terms are just supposed to constantly be negative 11. So what would the term be when I is 1? Well, it would be negative 11. And then you're supposed to add what you'd get when the term would be when I is 2. Well, it would still be negative 11. And when I is 3, yep, you'd still get negative 11. So I'm hoping that you summed these up to be negative 33. There we go. Now there's a property that you could use instead, and I hope that this particular property makes a ton of sense. If the other properties don't make as much sense, that's probably okay, but this one should just like feel true. So the property that goes with what we did there is if you have the sum as I goes from 1 to any upper bound, notice that this sum does start at 1. All the properties we're going to do here, your lower bound will be 1 of a constant. So I'll just let K represent a constant. Then in, like, for example, with part A, you ended up with 3 negative 11s. Well, if in this situation, you'd end up with n Ks. So you simply multiply the upper bound by the constant if you are in a situation just like this. So, and this is a property that we have mentioned in the past. So it's time to either memorize it or rememorize it, depending on what situation you're in. But you do want to go into your problem set with all the properties that we mentioned here, nice and memorized. So anyway, so a quick illustration as to how this property could be used would be the example that you had for part A over there. The sum as I goes from 1 to 3 of negative 11. You would just take the upper bound and multiply it by the constant, and you'd get that negative 33 that we got with if in doubt, expanded out. There you go. And with a lower bound, with a small upper bound like that, like 3, you know, it's kind of silly to need a formula for it, but we're going to be doing problems pretty soon where you have really high upper bounds, like 3,000 or infinity, you know, big upper bounds. So, all right, part B, let's show what it looks like for part B if you just use if in doubt, expand it out. Your first term is 1, second term is 2, third term is 3, and so on until you get to the end. Since your upper bound is 12, your last 3 numbers would have been 10, 11, and 12. So from there, if you don't have a formula for it, you could still think it out. In this case, your first and your last term add up to 13. Your second and second to last are 13, etc. So you basically have a whole bunch of pairs that add up to 13. And how many 13s would you have? Well, you have 12 terms, and so that would make 6 pairs of 13. So hopefully 6 times 13, which we'd end up with 78. So not exactly if in doubt, expand it out, but kind of, right? So what's the property that goes along with that one? The property that goes with that one is for the sum as I goes from 1 to n, where your terms are just generated with a rule like I. So let's just kind of like, you know, kind of do some metacognition on how we got the 6 times 13 over here. The 6 was the number of terms divided by 2. So in general, you would just take your number of terms and divide by 2. And then the 13 was just your first term, which in this case would always be 1. And then in adding 12, which was your last term. And so in general, that would just be 1 plus n, like so. Now this property, you won't see it written like this. You'll see it written like n times n plus 1 over 2, which for our purposes is actually going to be a bit neater. And so let's have you memorize it that way. So the sum as I goes from 1 to n of I is equal to n times n plus 1 over 2. Okay, and I'm going to put a memorization cloud around that, and you want to memorize that. Okay, now quick memorize it, and then as just an illustration, let's just kind of redo part B there. So the sum as I goes from 1 to 12 of I. If you use this formula, you would end up with 12 times 12 plus 1 over 2, which cancel the 12 and the 2, you get 6, and then times 13, and there's your 78. So what I'm trying to illustrate with this warm-up is how to get the answer kind of organically with sort of if in doubt, expand it out, maybe a little strategy. And then on the right side, how to get the same answer by using what's called an extrinsic formula. So these extrinsic formulas are where you don't have to do it term by term. You can just plug in the upper bound in a certain way and get the answer. Okay, and any formula I put in the bubble, you got to memorize. Okay, part C, if in doubt, expand it out, pretty basic. You'll have 1 squared, which is 1, plus 2 squared, which is 4, plus 3 squared, which is 9, and then you could just add it up, and I think you get 14 for that one. All right, which I wouldn't want anything fancy for that one because that one was so easy. You could even just kind of do it in your head. But man, oh man, as soon as this upper bound is much higher than 3, you know, if it was 33 or 333 or something, then I'd want a different way to go about it. So let's talk about an extrinsic formula for that one. So the sum as I goes from 1 to n of I squared, specifically when your rule, where you're adding up basically this, like the sum of all the squares. All right, the rule for this one would be n times n plus 1 times 2n plus 1 all over 6. Oh, goody. So that one's one of the harder ones to memorize. And how do we know that's true? Well, that's the kind of thing that in the previous section we would have proved by mathematical induction. But in this section, we're just expected to memorize it and to be able to apply it from memory. So just a quick illustration of that one. Let's redo part C over there from the warm-up using the formula just to kind of show that it works. So we had the sum as I goes from 1 to 3 of I squared. And if you were to use this formula to get the answer, you just put 3 in for all the n's. So you'd have 3 times 3 plus 1 times 2 times 3 plus 1 all over 6. Which would simplify down to be 3 times 4 times 7 all over 6, which would end up being 2 times 7, which is 14. There you go. And I'm not saying that for that particular problem, you're better off with the formula, but I am saying that pretty soon you'll be better off with the formula. All right. Part D, the sum as I goes from 1 to 4 of I cubed, just if in doubt, expand it out, would give you 1 plus 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. And good times, I think adding this up, we get an even little 100, which is super cute. And the property that goes with this one would be the sum as I goes from 1 to n of all the cubes. And the extrinsic formula for getting the answer for this one is n squared times n plus 1 squared all over 4. Which, if you look back at the sum of all the i's up here, it's just that right side of that rule, just with everything squared. So that's kind of cute. And you should memorize it. There we go. Okay. So let's just kind of rework part C, but using the formula. So we'd have the sum as I goes from 1 to 4 of I cubed. And if we'd use the formula, we'd just be popping 4's in for all the n's. So we'd have 4 squared times 4 plus 1 squared over 4. This 4 cancels one of these out. You'd be left with 4 times 5 squared, which is 25, which dun-dun is 100. There we go. Okay. Part E. Whoopsie. I was hoping that part E would remind you of a property that you've had before, where, you know, if you start expanding it out, then you just have like 7 times, 1 cubed, I guess, plus 7 times 2 cubed, plus 7 times 3 cubed, plus 7 times 4 cubed. And then I'm hoping that if you think of it that way, you'd be really tempted to just factor the 7 back out. And then you'd have 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed in there. And then if you write this back in sigma notation, you could see that you basically can factor constant multiples, constant factors. You can kind of factor them out in front of the sum. So if you put Humpty Dumpty back together again, you know, there you have it. So what I was trying to remind you of here for part E was something that we had mentioned back in the day, back in chapter 8 when we first learned about sums. It's the constant multiple rule for sums. So if you have the sum as I goes from 1 to n of a constant times a function of I, like in this case, the function of I was I cubed, you could pull the constant out in front and then evaluate the sum with the function of I in there, which typically kind of, that's a little good property to be reminded of, because sometimes it makes it so you can use the properties that we're having you memorize to the right here. So there you go. There are other properties for the sum formulas, but it's just the ones in the clouds here that'll have you memorize. So, you know, there's a formula for the sum as I goes from 1 to n of I to the 4th. And there's a formula for the sum as I goes from 1 to n of I to the 5th. And I'm sure there's one for I to the 6th and I to the 7th and all that. But I wouldn't expect you to have these higher powered ones memorized. I would expect you, however, to be able to like look them up and use them. So anything in the clouds that you see here are things I want you to have memorized, but something like the sum of all the I to the 4ths, I would just want you to be able to look it up and then plug an n in the right place and do that. So just for the record, this beast is what you'd use if you have I to the 4th as the definition of your terms, and then that monster would be the sum of all the I to the 5ths. So there you go. Okay. Before we do the next example, you should study all the properties that we have in the bubbles here and try to make sure you've got them from memory. And then once you do that, then see what you can do here with example 1. It says evaluate each sum and see how many you can do without having to look up any formulas. Good luck.